Hi, the title of this lecture is File System Implementation. In this lecture, we're going to study the very simple file system, and we are going to look at the details of undisk structures and how they are accessed, and how we can save the number of IOs associated with the file system operations. So this is the items of the list we're going to talk about. How can we build a simple file system, and what kind of structures are needed on the disk, and what do they need to track, and how they are accessed. These are the topics of the lectures in this video. So first one is what types of data structures are utilized by the file system? The data structures. So data structure is the most fundamental components of building a software, and how the file system organizes its data and metadata. And we are looking at the details of open, read, and write operation. This is the ideal very small storage device. There are 64 blocks. There are block size 4 kilobyte, and blocks are accessed from 0 to n-1. So okay, so there are 64 blocks. So the block size is 4 kilobyte. So the size of the storage is 4 times 64. This is very tiny storage device, 256 kilobyte. So among the 64 blocks, we first have to, this is what we call the file system partition. From beginning to the end, this is what we call a file system partition. And then we're gonna use, among these 64 blocks, we try to allocate 56 blocks to store the user data. Let's design the file system, and we allocate a section of file system partition as a data region. And there's going to be 56 blocks for the user data. Okay, from block number 8 to block number 63. So, okay, so now we have successfully made a big decision that we are going to allocate from block number 8 to block number 63 to the data region. Then what is the next step? We need data structure to represent a file. Then what kind of attributes do we have to represent a file? First of all, of course, the size. Oh yeah, there is. The size of a file. And who is the owner? Or permission. Permission means can this file be read, can be read, or can be written, or can be executed. This type of things. And more importantly, whatever data structure it is, the data structure that represents a file should contain an information about the data block that comprises a file. This data structure is usually called an inode. And inode is originally derived from the term index node. And index node is derived from the concept that there is a node and there's an index. And each index points to the data block that comprise a file. So that's what the inode is for. Okay. So we have to have an inode. This is inode. So a single file, every file has an inode. So in a file system, the number of files in the file system is the same as the number of inodes in the file system. So in this virtual some simplifier system we are designing, we have allocated 56 blocks for the data region. So this data region will contain, this data region here and here will contain one or more files. Okay, and then in our design, let's assume that we have to make a decision that we are going to allocate a region of file system partition to hold the inode. So there is an array of file system blocks, and each block will contain only inode. So for example, let's assume that inode size is 256 byte. And then we have 4 kilobyte block. So a single block can hold up to 16 inodes. All right, so we have to make a decision on how many blocks do we have to allocate to hold the inode. That question is directly relevant to how many number of files are we going to allow in our file system. Okay, let's assume that we make a decision, and then we decided to make the maximum number of files in this file system corresponds to 80. So there are 80 inodes. Then we're going to define the 80 inodes. Then since each block can hold 16 inodes, so we can dedicate 5 blocks to hold the inode. All right. Okay, so we are going to allocate from block 7 to block 3 to block 7 as the inode. All right, then what's next? We have defined data region, and we have defined the inode region. Let's say this is inode region. Inode region. Inode region. Since the inode region consists of the array of inodes, it is also called as the Inode Table. This is also called as Inode Table. Okay, so we are done with defining the data region and for defining the inodes. Okay, let's move on to the next step. What do we have to do? All right, next thing we have to do is there is an array of inodes and array of data blocks. The next thing we have to specify in our file system is to determine whether the inode, the data blocks, are free or allocated. Okay, there are a variety of ways to determine whether a block is free or allocated. For example, for some file system, you can allocate a certain section of block individual. We can allocate a certain section of individual block, for example 8-bit, and mark a special bit stream on this part to determine, to specify whether this block is being used or not. In our virtual file system, though, we're going to use a bitmap. So we are going to dedicate 1 bit for each data block to show that it is being used or not. So if bit is free, bit is 0, then it means that the associated block is free. If the bit is on or bit is 1, then it means that the associated block is in use. So there are we have to have two types of bitmap. First bitmap is for the data region, and we have the second bitmap for the Inode table. Okay, so because we have 56 data blocks, we need 56 bit. For Inode, because we have 80 inodes, so we need 80 bit for Inode bitmap. So these are two bitmaps, 8 bit and 250. Sorry, 56 bit for data bitmap and 80 bit for Inode bitmap. So this is our implementation for the bitmap. However, in our implementation, we decided to dedicate a block for each bitmap. So one block for data bitmap and one block for Inode bitmap. So we are allocating one block for data bitmap and one block for Inode bitmap. It's too much, right? One block is 4096 byte. That's 4 kilobyte. However, for Inode bitmap, we are using 10 byte out of 4096 byte. For data region bitmap, we are using just 7 byte because we are out of 7 byte out of 4096 byte. That is quite a wastage. Of course, you can merge these two and put it into a single block. That's for sure. But for this file system, we just decided to do that. We decided to allocate a single block for each bitmap. Data bitmap, 1 block. Inode bitmap, 1 block. Okay. All right. Then we also have to have information about the file system partition. So how many inodes are there in this file system partition, and how many data blocks are there in this file system partition, and what is the beginning block number of the Inode table and end block number of the Inode table, and beginning block number of the data region and end block number of the data region. All kind of information. And at the beginning of every file system partition, we maintain those information. This is information for a certain file system partition. We call it a superblock. So if the superblock is lost, we lost the organization of the entire file system partition. So if the superblock is corrupt, then in most cases, you lose the file system. That is the reason that most file system maintains 2 or more copies of the root block, superblock, in the file system partition. So when we register a file system partition, which we call a mounting of file system, the operating system will read the superblock first, initialize the various information. So we store a superblock at the very beginning of the file system partition. Of course, for many file systems, sometimes the file system maintains multiple copies of superblock. Something like here. Okay. So now let's look at the details of the Inode table. So each block is 4 kilobyte. It's 4 kilobyte and 4 kilobyte. Of course, for Inode bitmap, only the 7 byte will be used for bitmap, 7 byte, and data data block bitmap, oh sorry, inode bitmap is 80-bit. So this is 10 byte. And data block bitmap, it is 56 bits because there's 56 data blocks. So it corresponds to 7 byte. Okay. So these are data blocks. We have to, these are bitmaps, and these are these are the file system block dedicated for inode bitmap and data block bitmap. Okay. Then there comes an inode table. We have allocated 5 blocks for the inode table, and each block contains 16 inodes. So first block contains inode from 0 to 15, and then second block contains an inode from block 16 to 31, and the third block contains the inode numbered from 32 to 37. So every inode has its inode number. And inode number is an index in its inode table. So inode number 0 is the first inode in the inode table, for example. And inode number 32 is the 33rd inodes in the inode table. How can we find the location of the inode on the disk? Let's do that. So by inode number, we can calculate where the inode is on the disk. Okay. For example, if the inode number is 32, then we can calculate the offset of 32 in the inode region. It corresponds to the 32 times the size of inode, which is 256. So if you calculate the offset, then it corresponds to 8192. So inode number 32 is 8192 bytes apart from the beginning of the inode table. So because we know that the start address of the inode table is 12 kilobyte apart from the beginning of the file system partition, so we can calculate the position of the inode as the start address of the inode table plus the offset of the inode itself. So 8192 corresponds to 8 kilobytes. So if we take the summation of these two, then we can find the starting position of the inode number 32. So we can find the location of the inode number 32. Sorry, this is my watch. My watch has some vibration feature, and it asks me to move if I sit a chair for a long period of time. Anyway, let's move on. If we want to read inode number 32, then we first have to read the entire block from the disk. Okay, entire block from the disk, and once you load the entire block from the disk to memory, then you can extract the inode number 32. Now, let's look at the details of the structure of a file. So this is details of inode. This is inode. So it contains owners and timestamp. Timestamp means that it's access time, and it may contain the updated time, update, or modification time, change time, for example. So every time a file is accessed means file data block is read, then the associated field is updated. If the file system or file permission has changed, then change time is updated. If you update the data block in the file, then this field is updated. So there are a bunch of timestamps. For example, there are 3 timestamps in the Linux file system, ext4. And it also may contain the file size, and it may contain the number of blocks for a file. So number of blocks and file system file size is different, okay, because file size not precisely aligned with the block size. So file size can be, for example, file size can be 100 byte. But because most file system allocates a space to the file on block unit, the block contain number of blocks in the file corresponds to 1, and the actual amount of space occupied by the associated file corresponds to 4096 byte. So the file size stands for the amount of data contained in the file, and block count may refer to number of blocks may refer to the amount of data blocks occupied by a file. So that is slightly different. Okay, then how can we specify the data blocks associated with a file? Okay, Inode contains the location of the individual file that are associated with a given file. There are many approaches. There are many approaches in organizing file system blocks with a file. In this particular example, this inode allocates 3 types of pointers. Four types of pointers to specify the file block associated with the file. First one is direct pointers. Okay, so for a certain amount of pointers dedicated to directly specify the location of the data block. For example, we have allocated, for example, 10 pointers to specify the data block. For example, if there are 10 pointers, and we can address 10 times 4K, 4096, that's a 40K. So with 10 pointers, we can specify 10 data blocks whose amount corresponds to 4096 bytes. Okay, of course, 4096 bytes is slightly smaller than represent a file. So it allocates another pointer, but this pointer points to the pointer block. And that pointer block contains a pointer to the data block. Okay. So in that case, this pointer is called single indirect. So via using single indirect block here, let's say block size is 4096 byte. And so if there are 4 byte pointer, then there's going to be 10,024 pointers in a block. So with a single indirect pointer, we can point 10,024 times 4 kilobyte data blocks, which is 4 megabyte. Okay. So with a single indirect pointer, we can allocate 4 megabyte data blocks. Well, 4 megabyte data blocks can represent most of the MP3 files, but still it is a lot smaller than most video files, for example, a 2-hour video file can easily go over a gigabyte. So then this inode structure, we allocate another pointer, and that is double indirect block, double indirect pointer. So double indirect pointer points to the pointer block. It consists of single indirect pointers. So there are two level 3 true to address the position of the data blocks. So then the amount of data blocks it can address by these approaches 10,024 times 10,024 times 4 kilobyte, which is 4 gigabyte. Well, yeah, then by using a direct block and single indirect and double indirect, we can address using using double indirect pointer, we can address 4 gigabyte. Okay, and then on the same pattern, if there is another pointer, and we allocate triple indirect pointer, this is 4 terabyte. So using this type of index structure with a single inode, we can address up to 4 terabyte plus 4 gigabyte plus 4 megabyte plus 40 kilobyte worth of file size. Okay, then we can pretty much cover most of the file sizes. This is what we call indexed allocation. Of course, this approach is not without a problem. The disadvantage of this indexed approach is that when we access the first block, you can navigate through a single pointer. But when you access the last block of the very large file, you may navigate through multiple levels of indexes to reach the data block, which is very bad. Okay, anyway, this is the indexed allocation. Okay. Now look at the directory structure. A directory is a set of inode number, and a directory is a set of inode number and name pair. And however, this is abstract interpretation of data structure. But if you let's look at the details of the directory structure in VSFS, our file system, and ext4. So it consists of 4 fields. First one is inode number, and second one is record length, then string length, and actual name. So inode number is 4-byte integer, and record length is 4-byte integer, and string length is actual length of the file name. In most directory structure, first 2 block is dedicated for current directory and the parent directory. Okay, and then this each is called directory entry. Directory entry. And the size of the directory entry is aligned with the register size. It's 4 byte. So record length is multiples of 4 byte. 4, and here it's 8. And the next field is the length of the actual string. It's 2, 3, 4, 4, and 7. And this is the directory structure of VFS. And in ext4, there is inode number, record length, and length of the file name. And there is one more field called file type. The file can be a directory, or file can be a regular file. So that is a field to specify the file type. Now let's look at the details of file system operation. The first example is read. So we are reading a file. So for reading a file, we first open the /foo/bar. Okay. So how the file system accesses the file if we open the /foo/bar. First, we have to locate the inode of the root directory. Okay, so we have to read the root inode, and then after reading the root inode, then we have to read the data block for the root inode. After reading the root data block of the root inode, it will scan through the data block of the root directory, and then it will look up the contents foo. And if we find a contents foo, it will probably contain the inode number for a given file. Okay, and then using the inode number, the file system has to read the inode block of the foo. And then after reading the inode, we are going to read the inode for the file foo. And then we're going to read the data block for the foo that contains the directory entry, and then look up the directory entries and locate the inode for the file name bar and read the inode. Okay, then that's the process of opening a file /foo/bar. And then let's consider reading a file block from the bar file. So the read will have a parameter file descriptor of read. And then first it has to read the inode of file descriptor. And then from the inode, you will be able to locate the first data block associated with a given file. So you read the data block. And after reading the data block, you will be updating the most recent access time in the inode. So after reading a single block, the file system saves the updated inode to the disk. So if you look at this, the single read operation causes 2 read and 1 write. Okay. Opening a file bar updates issues 5 reads. It's quite a few, quite a lot. And if you perform another read, then you read the inode bar from the disk and compute the location of the second data block, and then read the associated data block, and then you update the most recent access time and write it again. So it issues 2 read plus 1 write. And after doing that, we read it again. Then we perform read and data block read and inode write. Again, 2 read and 1 write. So even for opening a file and reading a simple data block, it causes a lot of values. Let's look at the process of creating a file. File creation is one of the most IO-intensive operation. So let's create a file /foo/var. So there is root directory and there is foo directory, and under the foo directory you will be creating a bar entry here. So first you have to read the root inode, and then you have to read the data block for the root inode that contains directory entries for the root directory. And then by scanning the directory entries in the root directory, you will find the inode number for the foo directory. And then you will read the inode for the foo. And likewise, you will look up the data blocks for the foo directory, and you will read the data blocks for the foo directory. Now, after reading the data blocks for the foo directory, okay, you will be creating an inode for the file bar. To create an inode for the file bar, first we have to read the bitmap for the inode to determine the location for placing the inode. So you have to read the bitmap, and then you have to update the bitmap, specifying the location of the inode, and then you have to write it back. Okay. After updating the inode bitmap, so a new inode bitmap will contain the location of the newly created inode bitmarked. And then you will be adding bar entry, and let's say the newly created inode is 25. Okay, and this block is updated, and you write it back. And then since the data blocks for the bar has been updated, you have to read the inode of the bar, and then you write it back. So the newly created inode for bar will contain the initial size, initial permission, and data block location for the file bar, and you write it back. And then after you writing it back, you will be write the update inode for the foo directory again. This is right. So this is the end of the file creation. This is amazing, right? There are read 1, read 2, read 3, read 4, read 5. And then there are one write, second write, and third write. So creating a single file on the /foo/bar consists of 5 reads plus 3 writes. That's terrible, right? That's not good. There are too many IOs. Let's consider the following situation. You are using the cell phone to take a photograph, and you go out for a walk or hiking, and you take the picture on the flowers or birds or everything. Then people normally create like 300 pictures per day each time you go out, and then 300 pictures. If you upload the 300 pictures to your cloud, then your file system for the cloud will be creating the 300 pictures, the files for 300 pictures. So it'll be creating 300 files in the same directory. Okay, but let's consider 300 pictures, and you are creating 300 pictures, but there are 10 million smartphone users, and each of 10 million users creating 300 pictures per day. Then you will be the cloud file system has to handle 3 billion file creations per day. This is non-trivial amount of IOs, because if a file system performs 5 reads and 3 writes for each file creation, and you multiply this number with the number of files you are creating per day, then the pressure on the file system storage going to be immense. Okay, so let's think about writing to a file. In writing to a file, let's consider appending a block to a file. And then first you have to read the inode of the bar, and then you are writing a new block. So you have to first allocate a new data block. To allocate a new data block, you have to find where the free block is. To do that, you have to read the bitmap to find where the free block is, and then find a new free block and update the inode, update the data block bitmap and write it back. Okay. And then after allocating the free block, you write the updated data block back to the disk. If you write the updated blocks back to the disk, then various fields of the file inode will be updated. For example, file size, most recent update date, and stuff like that. So you have to write back the associated updated inode. So there are 2 reads and 3 writes for the write operation. And they same things. So if you write it again, then you have to read the inode and read the data block bitmap, and you write the updated data block bitmap back to the disk, and you write updated data block to the disk, and you write the updated data blocks. You write the updated inode. You do the same thing for the third write. Okay, so read the inode, read the data block bitmap, and update the data block bitmap, and write it back to the disk, and write back the updated data blocks, and write back the updated inode. So each write contains 2 reads and 3 write. That's huge, right? So what if we maintain the inode in memory, and we postpone writing the updated inode to the disk later? Okay, then you can eliminate this read, and you can eliminate this write. And of course, when you maintain the bitmap in memory, then every time you update a data block, you don't have to go to the disk and bring the new bitmap back to memory. Instead, you can read the data blocks, you can read the data bitmaps loaded in the memory, so you can eliminate this read. Okay. So depending on what kind of read-write policy or disk update policy you take, you can save large amount of IOs. So as we saw before, reading and writing is very IO intensive. Even though we read one file block, it requires some update on the inode, and it requires write to the disk block. File caching is an effective means of reducing the number of IOs associated with the file system operation. For example, there is a physical DRAM, and then you partition it and allocate fixed partitions of the physical page frame to cache the disk blocks. And this region is called buffer cache. Typically, the operating system has been allocating 10% of the physical DRAM for buffer cache purpose and use LLE replacement algorithm. But there are wastage of buffer cache, because not always all the frames are used. Okay, so 90% of the virtual memory is used for the page frame. 90% of the page frame is used for virtual memory to host the page from the process virtual address space. And 10% of the page frame is used for buffer cache. This is typical layout. Then to avoid efficient usage, we use page cache. We merge virtual memory and buffer cache. And so in page cache, a physical page frame can host a page in the process address space or a file block. So process uses page table to map a virtual page to the page frame. So process uses page table to map a virtual page to the page frame. And each file maintains a certain data structure to map a file block to the physical page frame. In Linux, data structure that is responsible for those kind of mapping is called address space. In that case, entire physical frames are dedicated for page cache, and some part is used for hosting the page in the process virtual address space, and some part is used for hosting the data blocks for the file. So this is usage of the page cache, and via using page cache we can eliminate the wastage of the space. So they use dynamic partitioning. Let me summarize the lecture. In building the file system, you have to specify a number of information. So information for a file, we have used an inode. And as a structure of the file, as a way to organize data blocks associated with the file, and in our VSFS implementation, we have used indexed file organization, which contains direct pointer, single indirect, double indirect, and triple indirect pointer. And in our directory, a directory is a data structure which map a name to its inode number. We implement a directory as an array of inode number and name pair. And for free block information, we need use bitmap. You should not be bound to this data structure. For example, when representing a file structure, you may want to use different data structure other than indexed tree. For representing a directory, instead of using an array of inode name pair, you may consider a different data structure such as b+tree or redx tree or red black tree. Of course, in specifying each block is being used or not, you may want to use different data structure other than bitmap. So in designing a file system, all are flexible. So that's the beauty of the file system design. That's the end of the class. Happy OS.